Hello, welcome back to KIC'S tutorials. In our last class, we discussed dihybrid inheritance, and we talked about the dihybrid ratio, which was 9 to 3 to 3 to 1, and we talked about how this ratio comes about. That's when you cross two parents with two pairs of contrasting characters, and then you cross their F1 offspring to get the F2. So the 9 to 3 to 3 to 1 ratio is found in the F2 dihybrids. So I told you that we'll be talking about modifications to the dihybrid ratio. So that is what we'll be discussing in this class. But before we start, stay tuned. Alright, welcome back. So today we'll be talking about modifications to the dihybrid ratio. Modifications to the dihybrid ratio. That is the 9 to 3 to 3 to 1. Alright, there are three factors that can cause modifications to the dihybrid ratio. We have codominance, incomplete dominance, and lethal alleles. So this 9 to 3 to 3 to 1 ratio is only found where there is complete dominance. That is, there is dominance and recessive relationship between the alleles at the two gene loci. Loci is spelled this way. And it is the plural form of locus. And I told you in a previous video that locus refers to the location of a particular gene on a chromosome. So let's say this is the chromosome, and this is where this particular gene is its homologous chromosome, and this particular gene has another allele. Probably if it were a flower color, this would give blue, as I've put here, and this would give red flower color. So just an example. So this is the locus for this particular gene. These two are the loci for this particular singular gene. So let's assume that in dihybrids we are considering two genes. So when you're referring to these two genes, you say loci, but when it is one, you say locus. All right, that is it. So, like I said, in dihybrids, when there is complete dominance, or there is dominance and recessive relationship between the alleles in the two gene loci of the parent, you get this ratio. But when there is no complete dominance, where we have incomplete dominance and codominance and lethal alleles, which can bring about the death of the carrier, then you have modifications to this ratio. So I'm going to be starting with the first modified ratio. Is this 1 to 2 to 1 phenotypic ratio. Okay, for this ratio, what brings about this ratio is one, when in the F1 dihybrids in the parent, you have dominant recessive alleles in one gene locus and codominant alleles in the second gene locus. Remember, in dihybrids we are considering two genes with two contrasting pairs of characters. So this is what brings about this modification. There's dominance genes or alleles in one gene locus and codominant alleles in the second gene locus. So now I'm going to give us an example to show how this works so that you can understand it. Okay. For instance, in cattle, we have the hornless condition being dominant over the horned condition. So let me use these alleles as examples. This is dominant over this hornless and horned. So let me write it as this. Hornless. This would also give us hornless since there is dominance here. Hornless. We have the horned phenotype. Okay, for this particular gene locus, this is dominant and this is recessive. Now for the second gene locus, we have white coat color being dominant to red coat color, but being co-dominant, with the red coat color, whereby you have an intermediate color. If you were to get the offspring, you have an intermediate color. So white would be this, and this intermediate coat color is referred to as roan. And then we have the red coat color. So this is how it works. Let's say co-dominant alleles. And dominant recessive alleles. Okay, so now I'm going to be making the cross so that we find out how this takes place. So let's assume that the parents, which are dihybrids, would have this, and this is the first parent, can be the male or the female, it doesn't matter. And we have the second parent as this. Okay, their gametes would thus be this and this. So if these were to fuse, cross. These were to fuse, the F1 individuals would have this genotype. That is, all of them will be hornless and roan. Now, if you cross the F1 individuals to get the F2 individuals, these are the possible combinations that you will get. First, the F1 individuals will produce these gametes. This in combination with this, we have this. This combines with this, we have this. This combines with this, we have this. And this will combine with this to give us this. So these are the possible gametes that the F1 individuals will produce if you were to cross them. So these are the possible gametes. Now, since we've gotten this, now we're going to draw the Punnett square, because the F2 individuals are usually numerous. So this crossing method might be a bit confusing. So we use the Punnett square to simplify it. Now, since we have 4 gametes here, we are going to be drawing a 4 by 4 Punnett square. So we'd have it this way. Okay. This is to show that this is the male parent. This is the female, or the male gamete, the female gamete. Okay. So, since this is a 4x4 Punnett square, we're going to be multiplying 4. 4 times 4 will give us 16. So we're going to be having 16 boxes here. So if you check 1, 2, 3, 4. Yes, 1, 2, 3, 4. So there we have it. Now we are going to be combining these gametes to see the possible phenotypes and genotypes in the F2 individuals. So you can join me. Let's do it together. This will combine with this. We have this. This will combine with this. We have this. So I'll quickly do the rest to save our time. Yes, we have this. Remember, please, this can also come in this form. This, and also this is the same as this. So you see that here, they will still give the same phenotype. So this W, big W. We have big H, big W, small w. Big H, small w, small w. Small h, big W, small w. Small h, small w, small w. Okay, big H, small h, big W, big W. Big H, small h, small w, big W. Small h, big W, big W. Small h, small w, big W. Okay, big H, small h, big W, small w. Okay, next, big H, small w, small w. Small h, big W, small w. Small h, small w, small w. Okay, so we have it. Now I'm going to be writing out the phenotypes based on this key that we have here, so that it will be clearer to us. Let me use another ink. Yeah. Okay, so we have this as hornless, and this as white. Hornless, roan. Hornless, white. Hornless, roan. Okay, so hornless again, roan. Hornless, red. Hornless, roan. Hornless, red. Hornless, white. hornless, roan. Horn, that is this, white. Horn, roan. Hornless, roan. Hornless, red. Horn, roan. And horned, red. Yeah, so we are done filling this out. Now we're going to check the different phenotypes we have and their ratios. So let me write it down here. Please, I have to erase this. Okay, so we have the phenotypes, the genotypes, and their ratios. Okay, so let's take the first phenotype we have here, hornless white. We have the genotype as this. Okay, let's see if we have another phenotype, another genotype for hornless white. Yes, we have another here. Small h, big H, big W, big W. Hornless white. Yes, we have another one. Big H, small h, big W, big W. Okay, so we just have 3 for hornless white. So that gives us a ratio of 3. All right. The next phenotype we have is hornless roan. Okay, we have the genotype as this: big H, small w, big W. Hornless roan, yes. Small h, big H, small w, big W. Another hornless roan, big H, yes, big W, small w. Another hornless roan, yes. Small h, big W, small w. Yes, another hornless roan, big H, small w, big W. Yes, big H, small h, big W, small w. Okay, that's it for hornless roan. So we have 1, 2, 3, 4, 5, 6. The ratio is 6. So the next phenotype, hornless white. So we'll be checking the genotypes. Hornless white, small h, big W, big W. Hornless white. Yes. Big H, small h, big W, big W. Hope we're checking well. Oh, excuse me. Made a little mistake here. Sorry. Hornless roan. We have it here. We have hornless red. Sorry. Yes. Hornless red. Here we have it. So the phenotype, the genotype, sorry. Big H, small w, small w. Hornless red, yes, we have another small h, big H, small w, small w. Another hornless red, yes. We have big H, small w, small w. And that's all for hornless red. So we have 1, 2, 3. Okay, the next genotype after hornless red that we don't already have here, horned white. Okay, horned white, we have small h, big W, big W. Horned white. Oh, it's just one, so write 1 for it. So next, after horned white, we have horned roan. Okay, which would give us small h, small w, big W, horned roan. Okay. Another horned roan. Small h, big W, small w. And that's it for horned roan. So we have the ratio as 2. And the last after horned roan, we have horned red. And this is just here. So we have the ratio as 1, which is this small h, small w, small w. So here we see 3, 6, 3, 1, 2, 1. Exactly this ratio we have here. So now you see how it works. All right, then let's move over to the second modification. Excuse me, I have to erase this. But before we go to the second modification, I'll show you a shortcut of getting this ratio. So you don't have to, if you don't have enough time to draw this Punnett square, you can use this shortcut to get the ratio. Okay. Yes. So the shortcut is this. Since we have dominant and recessive alleles in one gene locus and codominant alleles in the second gene locus, this is just the method I used to teach you that if you were to multiply 2 separate monohybrid ratios, you get the dihybrid ratio. And the normal monohybrid ratio we have where there is complete dominance is 3 to 1. So if you multiply 3:1 with 3:1, you get this. So that is the same rule I'm using here. So we are going to get the ratio, the monohybrid ratio for dominant and recessive alleles, which is 3:1, and multiply it by the monohybrid ratio for codominant alleles, which if you watched the previous video, I told you it's 1 to 2 to 1. So I'll leave a link of the video in the description box where you can find the video so you can understand how these ratios came about. So if we multiply them, we'll be having 3 times 1, 3, 3 times 2, 6, 3 times 1, 3, 1 times 1, 1, 1 times 2, 2, and 1 times 1, 1. So, see, that gives us this ratio. So, let's move on to the next modified ratio. Okay, that is the 1 to 2 to 2, sorry, to 1 to 2 to 4 to 2 to 1 to 2 to 1 phenotypic ratio. Alright, now this ratio is caused by incompletely dominant alleles in the 2 gene loci of the F1 parents. That is incompletely dominant alleles at both gene loci. So this should tell you that here you're going to be having a blend. No, not actually a blend. Yes, you'll be having a blend in the phenotypes. So, yes, incompletely dominant alleles at both gene loci. Alright, so let's get to it. I'm going to be giving an example too, and I'll draw the Punnett square, but this time I'll be very fast. I might not be reading it out to save our time, but just follow me. Okay, in this example, like in snapdragons as a type of flowering plant, the red flowers are incompletely dominant to the white flowers, whereby you can get pink flowers, and then the broadness of leaf is also incompletely dominant to narrowness of leaf. So let's take the alleles as for red flowers and broad leaves, and white flowers and narrow leaves. Sorry, white flowers and narrow leaves. So these are our 2 key generation individuals. So if you cross this, you have these gametes. So if these fuse, all the F1 individuals would have red flowers, pink flowers, an intermediate shape or size, intermediate width of the leaves. Okay, now to get the F2 generation and therefore the phenotypic ratio, you cross the F1 individuals. Alright, so these are the gametes that will be produced. We'll have R to B, B, this and this, and this. So these are the possible gametes that will be produced by the F1 parents. So now I'm going to draw the Punnett square also to give us the possible phenotypes in the F2. Alright, so we have RB, Okay. We use this. Okay, so this is the female parent, and this is the male. Okay, so I'm just going to combine these gametes to see. We have here R, B, B. We have R here and B here. R here, B here. Okay. Let me draw this first. All right. So here we have R, B, R, B. Sorry, I'm taking this to write them out since I'm using different markers to save our time. Here also we have R and B. Same here. Okay, then the male gametes will fuse to give us R and B. We have R and B. R and B. R and B. So we have this. Okay, so here we have it. Now I'll write out the phenotypes so that we can know from what we had before. I told you red flowers. This would give us pink flowers since they are incompletely dominant, and white flowers. Okay, and then for the other parent, for the other gene, we have broad leaves, intermediate, and narrow. Okay, so this is what we'll be using to fill this out. Alright, so here we have red and broad. Red and intermediate. Here we have pink and broad. Pink, intermediate. Okay, also red and intermediate. Red and narrow. Pink and intermediate. Pink and narrow. Pink and broad. Pink, intermediate. White and broad. White and intermediate. Pink and intermediate. Pink and narrow. White and intermediate. White and narrow. Okay, so there we have it. So now we're going to check the different phenotypes we have and their ratios. Okay. Phenotypes. All right. So now the first phenotype we have here is red and broad. So we're going to check the genotypes that have that. We have this and this, red and broad. Okay, so this is only one. It gives us this. The next, red and intermediate. Intermediate, we have this genotype, big R, small b, big B. Red and intermediate, yes, we have another, big R, big B, small b. It's for red and intermediate. Okay, so two here. The next, which we don't already have here, we have pink and broad. Which we have as this, small r, big B, big B. Pink and broad. Yes, we have another. Okay, let's take it this way. Let's finish with red so that it will be easier for us. Right. So we don't get it conflicting. Oh. So we have red and broad, red and intermediate. We have red and narrow. Okay. So we're going to, we have one here. Small b, red and narrow. Okay, that's the only one. So 1. Now we're done with the red. Let's take pink and broad. Okay, let's find out. Yes, we have it here. Pink and broad. We have another pink and broad. Okay, that is it. There's 2 for this. Next, pink and intermediate. So we have 1 small r, big R, small b, big B. Pink and intermediate. Another small r, big R, big B, small b. We have pink, right? Pink and intermediate. Pink and intermediate. Pink and intermediate. We have another pink and intermediate here. Yes. RR BB. So another pink and intermediate. Okay, and that's it. So we have 1, 2, 3, 4. So then pink and narrow. So pink and narrow, we have here. Yes. Small r, big R, small b, small b. Pink and narrow. Yes, we have another. Big R, small b, small b. Pink and narrow, that's it for pink and narrow. That's 2. So we're done with pink. Now we'll go to white. White and broad. So we'll find out white and broad. We have it here. Small r, big B, big B. White and broad. Oh, and that's it for that. We have 1. And then we have white and intermediate. Okay, white and intermediate. Yes. Small r, small b, big B. White and intermediate. Yes. Small r, big B, small b. That is 2. So the next will be white and narrow. White and narrow. So only 1. R, B, B. So if we look at the ratios, you have this. It can be rearranged due to how you arrange the phenotypes, but it's basically this same ratio. So that is it for this ratio. But before I go, I'll also use the shortcut I used in the first ratio to help us get this ratio. So we have incompletely dominant alleles at both gene loci in the F1 parent. So we're going to get the monohybrid ratio for incompletely dominant alleles, which is 1 to 2 to 1 times, since it is at both gene loci, 1 to 2 to 1. This is for the first gene locus and this is for the second. So we'll be multiplying that. 1 times 1 is 1. 1 times 2 is 2. 1 times 1 is 1. 2 times 1, 2. 2 times 2, 4. 2 times 1, 2. Next, 1 times 1, 1. 1 times 2, 2. 1 times 1, 1. So here we see we have this ratio. All right, the next ratio, the third ratio, is okay. So this ratio is brought about by dominant alleles in one gene locus and recessive lethal alleles in the second gene locus. Remember, recessive lethal alleles or lethal alleles cause the death of the carriers. So, well, simply, we won't be doing this cross to save us some time. I'm just going to be using the shortcut, but make sure you find questions that can help you understand this. All right, so we get the monohybrid ratio for dominant alleles, which is 3 to 1, and the monohybrid ratio for lethal alleles, which is 2 to 1. We'll be multiplying through. So 3 times 2 is 6. 3 times 1 is 3. 1 times 2 is 2. 1 times 1 is 1. So here we have it. Now to the next ratio, which would be the fourth. We have 2 to 4 to 2 to 1 to 2 to 1 phenotypic ratio. This is caused by co-dominant alleles on one gene locus and recessive lethal alleles in the second gene locus. So we get the monohybrid ratio for co-dominant alleles, which is 1 to 2 to 1. And the monohybrid ratio for lethal alleles is 2 to 1. And then we multiply. So this can also be turned around. Let me write it this way. Even though it will give the same ratio but a bit mixed up, but I don't want you to be confused. So recessive lethal alleles and co-dominant alleles. So that's 2 times 1, 2. 2 times 2, 4. 2 times 1, 2. 1 times 1, 1. 1 times 2, 2. And 1 times 1, 1. So here we have it. If you exchange it the way I wrote it before, this will be mixed up, but just know it's the same ratio. Okay, to the last ratio for this class, we have the 4 to 2 to 2 to 1 phenotypic ratio. This is caused by recessive alleles at both, recessive lethal alleles at both gene loci. So just like we did in others, we get the monohybrid ratio for recessive alleles, which is 2 to 1 times 2 to 1. So multiply it. 2 times 2 is 4. 2 times 1 is 2. 1 times 2 is 2. 1 times 1 is 1. So here we have it. As simple as that. But like I said before, and I'm emphasizing, please look for study questions that can help you understand this. Make sure you draw the Punnett square and do what I just did so you understand how it works, so that you don't end up trying to memorize and then it will fail you when you need to reproduce what you've memorized. All right. Now, I'll have you know that it is not only co-dominance, incomplete dominance, and recessive alleles that can cause modifications to the dihybrid ratio. Epistasis and other types of gene interactions can cause modifications to the dihybrid ratio. And that is exactly what we're going to be discussing in the next class, that is interaction of genes. So if you like this video, please don't forget to hit the like button, share this video with your friends. If you have any comments, questions, leave them in the comment section. And if you've not subscribed to this channel, please don't fail to subscribe and hit the notification icons so that you can get updates whenever we post a new video, as we post videos on Wednesdays and Sundays. So until the next class, see you.